All right, everybody, I think I'm going to go ahead and get started here. It's about 10 o'clock. Welcome and good morning. I hope that you're doing well today so far and having a good week. I guess we got another heat wave coming. Maybe not as bad as the one last month, but it's going to be kind of hot this weekend. So hopefully you can enjoy some air conditioning and get some linear algebra done in the process these next couple days ahead. Just a quick couple of announcements, then I want to jump right in today. We have a lot to do today. There is a homework assignment due tonight. I see a few folks have got some problems on the side board for me there. I'll see what amount of time I have for those. I haven't had a lot of people come into my office hours lately, so if it may be that today is the day that that has to happen because I do have a lot to cover. I may not have a lot of time to do those homework problems, but it's an important assignment. I definitely encourage you to try to give it your best effort, and by midnight tonight, that's when you need to get that submitted for me. That's about all I got right now for announcements. Does anybody have any questions about any of that before we jump in? Don't forget, you can come to my office hours either in person or in Zoom. I have hours starting at 5:30 today, which is after my last class, and I'll be around all evening until 10 o'clock with about a 1 hour break at 7 o'clock. Other than that, you should be able to catch me pretty easily, either in person or in Zoom. So hope that you will take advantage of it if you need it. This is chapter 4. This is always a sort of a pivot point in the semester where everything gets a little more abstract and doesn't feel quite like math anymore at times anyway. So if you're finding it to be a little bit strange and get a little tough to get used to, you're not alone. It happens every semester I do this, and all I can say is I'm here to help. I'll do my best to be available and give you some help with trying to master this stuff. Yeah, so let's remember where we were on Tuesday here, and then we'll pick things up. We've been talking about vector spaces, and we've got some nice examples of vector spaces already in our possession. We know about matrices, we know about calculus functions, we know about polynomials. Another good example of a vector space is just Rn, right? The traditional physics vectors in n-dimensional space. So we've got this idea of a vector space, which is just a big universe where some abstract problem is happening. And within that vector space, we can talk about subspaces. These are just vector spaces within the bigger universe that they're sitting in. And what you can think of is that there's lots of subspaces of a given vector space. And in fact, there's a very easy way to make a lot of subspaces, which are vector spaces inside of V. Namely, we can simply grab a handful of vectors and form their span. Whatever that is, whatever that consists of, will be a subspace of V. But what are you doing if you take the span of a set of vectors? Now you're just throwing in all possible linear combinations of those vectors, right? You're just throwing them into your bag. So you're making a bigger set that has all of these linear combinations in them. Linear combinations, remember, just looks like this, right? C1, V1 plus C2, V2 plus C3, V3, and so on. The C's are just scalars, and you're doing scalar multiplication and addition. And that's the two operations you have in a vector space. And you're just combining vectors in that fashion. You're just collecting all of those linear combinations. And whatever that is, whatever that ultimate collection of vectors is, it's called the span of those vectors. It always forms a subspace, meaning that it is a vector space in its own right, just within the bigger vector space V. Right. So that's a cheap way, an easy way to make a subspace. If you were trying to make a subspace, all you got to do is grab some vectors and form their span. Everybody in this room could grab a different handful of vectors and make a different span and have a different subspace. That would be perfectly fine. So there's lots of subspaces to a given vector space, right? That's certainly the case. Now, one thing I didn't mention so much on Tuesday is that when you take this handful of vectors and you form their span, you take all possible linear combinations, it's actually possible that the span of all of those vectors could in fact be every vector in the vector space. It could be equal to the whole big universe V. That could happen. I mean, actually, as a quick example of that, don't worry about writing this down because I'm going to have a lot more notes on this in just a few minutes. But if I just took the points 1, 0, and 0, 1 out of R2, if these were my two vectors, V1 and V2, and then I took the span of those vectors, what would be the span of these vectors? Well, it would just be every possible linear combination of these two vectors. You would form all such expressions. And when you simplify that, you actually get, an arbitrary point of R2 with two random entries that could be anything. So it's actually the span of these two vectors is the entire R2. That can happen. That can happen. And if the span of the vectors that you've grabbed happens to be the entire universe V, then we're just going to say that those vectors span V. That set spans V. Or another way of saying it is that those vectors are a spanning set for V, right? So these are just two ways of saying the same thing. The set of vectors spans V, or in other words, it forms a spanning set for, oh, I wrote S there. That should be V. Sorry, typo. That should be V. A spanning set for V, right? Good enough? Okay, so we are still in section 4.4, and there are two skills that everybody has to learn how to do in this section. Okay, I want to spell it out for you. Two things we need to be able to do. The first one we have not talked about yet, so we're going to do that today, which is that if I give you a set of vectors, we need to be able to decide yes or no, do those vectors actually span V? Do they form a spanning set? So like right here, the vectors 1, 0, and 0, 1, yes, they do span R2. So that would be a yes on this little baby example over here. But I said see below because it's not in your notes yet. We're going to come back to this question A, or this skill A, in just a few minutes. But the one that we actually did start talking about last time is this second item here, this second skill, which is item B. If we have a subspace of V, could be V itself, or it could be some smaller subspace within V, we want to be able to actually find a spanning set for S. So if S is just any subspace of V, it'd be nice to find a spanning set for that. So on Tuesday at the end of class, we found a spanning set for the 3x3 skew symmetric matrices. You may or may not remember that. That one should be in your notes. If you go back and refresh your memory, the 3x3 skew symmetric matrices, we found a spanning set for those. How did we do it? We followed this three-step process. What's it say? We write the general form of a vector from the space that we're looking at. Then we bust out the variables. And finally, we list the vectors that are left over after we've done that busting out process. It was a three-step process. That's how you find a spanning set for any subspace. Okay? So if you can do these two things, these two skills, you are in great shape in the topic of spanning sets, section 4.4. So we haven't talked about how to do A yet. I'm going to do that in a moment. But I want to start by warming up with a couple of examples that are related to B. So this is skill B, which is the one that we have sort of talked about already once on Tuesday. I'd like to come back to it now. And these These types of questions are all over the material here in chapter 4. You're going to see a lot of this kind of stuff. So let's try to do this. Let's try to warm up with this. In both cases here, I have a big universe. I have one of my big vector spaces. On the first one, I'm going to do matrices that have a size of 3 by 2. And then in the second one, I'm going to do polynomials of degree 3 or less. So we'll see a couple different examples of how this would look on paper. And in each case now, I have written down a subspace. Now, I want you to take it for granted that it is actually a subspace. I'm not going to stop and check that it's closed under addition and closed under scalar multiplication this morning. We practiced that a lot on Tuesday in the group work and in some of the examples we did. So take my word for it, guys, that these two sets S do in fact form a subspace. Now, I should point out that you see the zeros here on both of these problems? If I tried to change either one of those, please don't do this in your notes, but let's say I tried to change this and say, I want to talk about the matrices whose 6 entries add up to 1. Then you wouldn't even have a subspace, right? Because after all, what is the 0 vector in the M3 by 2 world? This is the 0 vector of that vector space, and it's not part of S anymore because the 6 entries of this matrix do not add up to 1. So this guy would not be in S the way I've set up the S right now. And guys, if you don't have a subspace, then you can't find a spanning set for it, right? Read what B says, given a subspace. Okay, so if you don't have a subspace in the first place, you're not going to be looking for a spanning set. So I've got to make sure that my S really is a subspace. But as I said, as long as this is a 0 right here, things will be just fine. The 0 vector check will pass. And I'm not going to spend the time right now, but you could verify that in both cases, these sets are closed under addition and scalar multiplication. Which is, remember on Tuesday, that was the main thing we said. A subspace inherits most of the vector space rules from the big universe V, but you do have to check that it's closed. It's closed under addition and scalar multiplication. Okay, anyway, enough about that. We're going to assume that these are in fact subspaces, and our job is to find a spanning set for them. So let's start working on the first one here. So be good practice for us, and eventually we'll do some group work and some homework next week for you guys to practice it a bit more for yourself. But let's do the solution to number 1 first of all here, okay? So we have our 3-step process. Because we're working on item B here, if we want to find a spanning set for S, the first step is to write the general form of a vector in S. Now that is going to be, in some ways, the most challenging part of the whole thing is we have to write down, well, what would a vector in S look like? Obviously, it's a 3 by 2 matrix, right? It's a 3 by 2 matrix, so you can give yourself, so I'm now starting on the 3-step process with item A. So I'm going to write down a 3 by 2 matrix. And of course, so don't write this down yet, just kind of follow me along here for a minute. Of course, if I wanted to fill in this matrix randomly, I would do it like that. And that would be what a 3 by 2 matrix would look like. But we have this condition here that the 6 entries of the matrix have to add up to 0. So we have to tweak this format so that it's kind of obvious that the 6 entries are adding up to 0. And the way I like to think about this is, I like to imagine for a minute that somebody asked me to write down a 3 by 2 matrix whose entries add up to 0. And you know what my thought process would be is, well, I can do anything I want in 5 out of the 6 entries, as long as the last entry, the last number I fill out has to cancel everything else out so that it actually adds up to 0. So the form that we would want to use here, and we actually should probably make even a little bit more space for this, but the form that we would want to use for this, and now this you can write down, is that it would be something like this. Everybody read that okay? This is just the last entry of the matrix is just the negative of all of the other entries added together. Now here you have a matrix whose 6 entries add up to 0, and it's kind of what I would call the general form of that. You see? Now, there's nothing that says you have to use the letters A, B, C, D, and E. If you use X, Y, Z, U, V, that's fine, right? The exact choice of letters. But you should be using letters here, variables. After all, the next step is going to be bust out the variables. So you should have variables appearing in the form of your vector here. But what you call those variables might not be the same as the next person, right? So it doesn't matter what letters you use. The other thing is there can be more than one right answer for this. So again, you don't need to necessarily write this down, but I just want to make this point that somebody could come along and say, you know, I want to do it this way, and I'm going to put the negative of all of these other entries right here instead. And this would not be wrong either, right? This is just a different preference for sort of where the 5 arbitrary variables are introduced, and then a different slot canceling them all out. That's also fine. Okay, but is everybody comfortable with this first step? Because this is actually, to me, this is the hardest part, just writing down the form here. Yeah.
Could you do like B is the negative of A and then D is the negative of C? Or is
Not
that, no?
necessarily. So that's a great point. What Julia is sort of saying is, well, couldn't we have done it this way? You know, couldn't we have decided that we wanted to write our matrix like that? I would agree that the 6 entries here do add up to 0, and that would be correct. However, this is not the most general form. There's nothing that says that the 2 numbers on the first row have to cancel out, and on the second row, and on the third row. If the set S had said 3 by 2 matrices where every row adds up to 0, then this would be what you would want to have as your form. But that's more restrictive than what this S that I'm giving you is saying. The S that I'm giving you is just, no, I don't care. Just all 6 numbers have to add up to 0. So you can do anything you want for the first 5 entries as long as the 6th entry cancels it out. Clear enough? This is something you guys are going to be doing a lot of. So definitely want you to be engaged with how this process is working. But yeah, the choice of the letters you use doesn't matter. Where you have your sort of last slot canceling everything out doesn't matter. But we do need this to be a very general form. It does need to be a very general form. Okie dokie. With that in mind, let's go to step B. Step B says bust out the variables. So once I've written down this form, the next thing I'm going to do, and this is step B of the process, please don't confuse that with the letter B in the matrix. I'm now going to bust out the variables. So I have 5 variables, right, to bust out. Let's bust out the A. Okay, so now how does that work? If I bust out the A, I go through the matrix here, and everywhere I see the A, I kind of leave behind whatever the coefficient is. So there's a 1A in the top left corner. There's no A's on the top right or in the middle row or on the bottom left, but then there's a -1 in front of the A that's in the lower right corner. You see there's a negative A there. And I'm ignoring B, C, D, and E right now. I'm just focusing on where do I see the A in this general form. All right, so I got my A busted out. Then I'm going to add to that. See, I'm not done. I have to go to the next variable, which is B, and I do the same thing again. I look in my general form, where is the B? Well, there's no B in the top left corner. There's 1 B in the top right corner, nothing in the middle row, and then in the bottom right corner, I have a -1 again. Okay, so I can write that down. And I'm going to keep going like this with all of my variables. The next one is C. Okay, so I bust out the C. That leaves me, there's nothing in the top row that has anything to do with C. Again, I'm looking over here to figure this out. The C is in the left middle entry, so there's 1 C there. then the only other place where there's a C is in the bottom right corner. And again, it has a minus in front of it. That minus sign is gonna show up with all of the variables actually. Okay, then we go again. We have another variable here, which is D. I'm gonna do the same thing again. Nothing, 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 but then there's one D in the right middle, and then again on the bottom right corner, there's a minus one. So D gets multiplied by that. And then finally, E. E is my last variable that I included here. And I have no E's anywhere on the first two rows, but there's one E in the lower left and negative one E in the lower right. This is busting out the variables. That's the idea behind that. Does that make sense? Everybody kind of following how that's working? Yeah, Alex?
So we wouldn't have to do the last one?
The last one meaning this
Yeah.
one? See, there's no new variable here, right? If there had been an F there, then of course I would bust out the F and I'd have another term. But yeah, we don't have to do anything else here. This should actually be mathematically correct. Like if you were to actually combine this right-hand side back together again, it should then produce exactly what you had over here. This is literally an equal sign. Yeah. Okay, so that's step B. And then the third step of the process is just to list the vectors that remain, and that is your spanning set. So let's go ahead and write it down. The spanning set would be equal to, so now I'm going to get out my big braces because I am writing down what a set here. And I'm just going to list the 5 matrices that got left behind on the right side in this linear combination. So we do have to write them all out again. The first one is just the one that was with the scalar A, and then comma. I'm making a list, guys. So in a list, you're going to use a comma to separate the entries. So we write down the second matrix, then we write down the third matrix, then we write down the fourth matrix, right? And finally, the last matrix, like so. So we're just literally copying down the answers now. So this is a spanning set for your subspace in this example. What do you think? Any questions on that? I think the hardest part is actually step A, getting the form of your vector written down correctly. Once you've got the form with the variables in it, busting them out is pretty natural, and then making the list is sort of just a bookkeeping thing, writing down the vectors that you've been left with. Okay, great. If everybody's good with that, let's try the second one. The second one is going to be a totally different universe, so everything's going to look a little different on the board here. We're going to work on number 2, we're going to work with polynomials in P3 of R. And what does it say here? S is the subspace where P of 5 is equal to 0. Again, if this was not a 0, if P of 5 was equal to 1 or something like that, it wouldn't have been a subspace. And if it's not a subspace, we wouldn't be finding a spanning set for it. Okay, so let's try to do the solution now to number 2. So let's see. Step A is to try to write down the general form of a polynomial that is in S. Now, I do know that it's a cubic polynomial, P3 of R. So normally the polynomial, if it is in P3 of R, is going to look like this kind of a expression. I'm going to go ahead and write it down. Okay, so that's kind of what P of X looks like. Actually, while we're on the subject, if the question had said, find a spanning set for P3 of R, well, then you would just be writing this down. You would be busting out your variables, and your answer would already be, I mean, the variables are already busted out. This is already a linear combination. If we were looking for a spanning set for P3 of R, we're already done. Because we write down the form of a cubic polynomial, right, using general letters. We bust out those letters, which is already done in the way that the form was written. And then we just make our list of the vectors, and the vectors would be these different powers of x. Right? But we're not being asked to find a spanning set for P3 of R. We're being asked to find a spanning set for S, which is polynomials that when you plug in 5, you get 0. So far I have not incorporated that anywhere into what I've done here. So this is not going to be the spanning set we're looking for. We're going to need to work a little harder to get it. Folks with me so far? Let's just see what does happen if I plug in 5 for x here. So P of 5, right? Because that's obviously relevant to the calculation. I'm still on part A. Still trying to get the form of my vector here. If I plug in 5 for x, right, then this is what I would get. 125a plus 25b plus 5c plus d. And the condition that we have here is that this is supposed to be equal to 0. So this is another one of those situations where you don't get to pick all 4 of these numbers however you like. Once you've chosen what A is and B is and C is, then D is forced. Or once you've chosen what D and C and B are, then A is forced. I can actually think of this as a little, linear system of equations, and if I want to, I can write it out kind of like we did back in chapter 1, or sorry, chapter 2, where we just put down an augmented matrix for our system. It's just that it's not really a very big system. It only has one equation in it. If I had given you something else here, if I had said, P of 5 equals 0 and P of 6 equals 0, then you would get a second equation here, and the matrix would actually have 2 rows in it. But as it stands, you pretty much have a single equation in a single row. And what you see here, guys, is that B, C, and D are all free. Those are all free variables because they don't have pivots on them. And then I can solve for A. So let's solve for A here. Maybe I'll do it. Let me do it over here. So if I solve for A, I'm going to get negative. I'm going to kind of skip a step here, guys, with the algebra and just kind of tell you what you get. So I'm solving this equation right here for A. So I'm going to move everything else to the other side of the equation. So it should be negative 1/5 of B minus 1 over 25 times C and minus 1 over 125 times D. Okay, I'm still on the first step. I'm still trying to write down what the general form, I'm trying to write the general form of a vector in S right. Okay, is everybody with me? Now, here's what I'm going to do. I'm just going to take this formula for A and plug it back in to my original P of X again. So now I'm going to write down my P of X. It's going to be the quantity of negative 1/5 of B minus 1 over 25 of C minus 1 over 125 of D. That's times x cubed. And then plus bx squared plus cx and plus d. And that, my friends, is actually the form that we've been looking for. This is the form of our P of X. If you now plug in 5 everywhere you see an X, I can promise you, you will get 0. Okay, so this here is not the general form for S. This is just a cubic polynomial. I have to incorporate the constraint equation here into this form. And that's what I've done here by replacing A by this messier looking coefficient. And that came from setting P of 5 equal to 0 and solving for A. So there's a little extra work there that we have to do. Okay, in the interest of keeping my recap up on the board for another minute or so, I think I'm going to come over here to do step B now. So step B, the next step is bust out the variables. Now, what are my variables here? My variables are B, C, and D here, right? Those are the letters that I see. So let's bust them out one at a time. I have a B. And B is being multiplied by, can somebody tell me what would be the term that goes with B? Blake?
Says negative x cubed over 5.
I like it. Negative 1/5 of x cubed plus x squared. Take a look. Here's a B that has a negative 1/5 x cubed on it, and then plus an x squared term as well. So that goes with B. Very good. Then let's do the same thing with C. Does somebody want to give C a try? What's the term that goes with C? Jason.
Negative x cubed over 25.
Okay, negative 1/25 times x cubed plus x. Very good. I like it. And then finally, we need to have a D term, because that's another variable that we see. Does somebody want to give the D term a try? Yeah, Kira?
Isn't it negative 1/5 x to the cube and then plus, oh, sorry, minus 1/125?
So I got my negative 1/125 x cubed. And where else do I have a D?
Would it be positive 1/125?
This is a minus. I'm right here right now.
Uh-huh.
This is the 125, but where else is there a D? Way over here. And is there anything in front of that?
No.
No. So this is just plus 1.
Oh,
Yeah. just a plus 1 on that. Clear enough? So that becomes your busted out. Here we have busted out the variables. And then finally, for step C, I write down my spanning set. I write down my spanning set, so I get my braces. I get my braces out, and I write down, the list of these vectors that are left behind. Negative 1/5 x cubed plus x squared, comma, negative 1/25 x cubed plus x, comma, negative 1/125 x cubed plus 1. And this would be the answer for the second warm-up question. Okay? Notice that if you plug x equals 5 into any of these, you will get 0. And that makes sense because after all, these are supposed to be polynomials that are in S. They're supposed to be in S, and in fact, they're supposed to span S. So of course, if I put in 5 for x here, I would expect to get 0 out of it. The other thing you might notice, remember when I originally said, what if we were trying to find a spanning set for P3 of R? And I said that we would just write this form and we would bust out these powers of x directly. Notice how many things do you have here that you busted out? 4 right here. How many things do you have over here now that we're looking at S that got busted out? Only 3. Only 3. So the original P3 of R busted out 4 polynomials. It took us 4 polynomials to span P3 of R. It actually only takes us 3 polynomials to span S. That's kind of reflecting the idea that somehow S is smaller than V. And we've seen that picture, of course. Here's V, and inside of V is S. S is not as big as V, right? And that's because there's a constraint. There's a membership constraint in S that sort of throws out a lot of polynomials that are not part of S. And so we should not be surprised at all that S is smaller than V, and we're able to span it with less vectors, right? I have less linear combinations that I need to make if I want to span S, as opposed to if I'm trying to span the whole V. You see? Oh, this is going to be a really important idea for us. The idea of how many vectors does it take to span your space, right? So P3 of R, it required 4 vectors to span the full universe of P3 of R. But if I'm only looking at some of the cubic polynomials, the ones that when you plug 5 into them, they give you 0, right? Now that's smaller and it takes less vectors to span it. it takes less vectors to span it. So that's kind of interesting, I think. Questions here? Yeah, Julia?
Why did you choose the denominators for A, like the reasoning behind it?
Well, I just solved this for A, right? So if I take this equation and I solve it for A, I'm gonna move all these terms to the right-hand side, and then I'm gonna divide through by
Okay,
125. That's where that denominator comes in.
thank you.
Mhm, sure. I mean, the truth of the matter is, if you had wanted to, you could have solved for D. If you had done that, then, you know, you would have a different form of your P of X. Your P of X would then not have B, C, and D down here. It would have A, B, and C down here. And that would actually also be correct. You can have more than one correct answer for this. It says, find a spanning set for S. Nobody ever said there's only one, right? There can be lots of ways to span S. But the reason that I chose to solve for A instead of solving for D is I want to leverage what we learned in chapter 2, which is that you circle your pivots, and then you set up your free variables and you solve for the leading variables in terms of the free variables. I didn't want to deviate from that because that's what we've just been doing for the last, 2 or 3 weeks now. And I want to be consistent with that. Guys, there is a lot of great stuff on this board here. You're going to get this kind of question a lot, finding spanning sets for a space. And that is this second skill. So we have now discussed item B here. Given a subspace, how do we find a spanning set for it? 3-step process, right? Write down the general form of the vectors in S, bust out those variables, and then just list the vectors that are there, right? That are left behind. And it's always that same process. Okay. So if everybody's okay with that, I would like to kind of turn to a slightly different question, which is the item A up here. This is the other skill that when we haven't talked about this one yet. And this one is saying, if I hand you a set of vectors, I would like you to decide yes or no, will it be a spanning set for the vector space? So I'm going to start with an example of that first, and we'll figure out how to sort this out as well. Okay. Great. So let's go back now and let's go back to skill A in my list over here. I've got my two main skills that I want everybody to be able to do from this section. So this is an example now to kind of illustrate what I'm talking about. And what this says is, here's my example, is the set of 2, -1, and 4, comma, 3 and -3 and 5, comma, 1 and 1 and 3, is that set a spanning set? Is that a spanning set for R3? So this is a yes/no question. It's a yes/no question, and we're going to try to answer that. So R3 is going to be the vector space, and I just want to know, do these 3 vectors span it? Again, let's put it in layman's terms. What does that mean? What it means is it true that if you take all possible linear combinations of these 3 vectors, that you could actually make any vector in R3? It's a yes or no. And just looking at it, I don't know the answer, right? But that's the question. Can I make every vector in R3 as some kind of a linear combination of these vectors? Let's just give these names, by the way. I'll call them V1, V2, and V3 here. Those are my 3 vectors for this example. And here is how we can think about this. For the solution to this, we can imagine that if we fix some point in R3, I'm going to call it ABC. I'm sorry, I don't want to call it ABC. I want to call it XYZ. It actually doesn't matter, but I think it'll be clearer if I use XYZ. So I'm going to use XYZ, which is just any point in R3. And then we can try. Again, I don't know if it's gonna be possible. We can try the following. We can try to do, C1 times the first vector, which is 2, -1, 4, plus C2 times the second vector, which is 3, -3, 5, plus C3 times the third vector, which is 1, 1, 3. We can try to see whether we could make that become equal to X, Y, Z. In other words, if I pull some random X, Y, Z out of R3, the question is, could I solve for C1, C2, and C3? The real question here is, can we solve? Can we solve for C1, C2, and C3? This is yes or no, right? This is a yes/no question. Can we solve for C1, C2, and C3? If the answer is yes, then we're going to say that our vectors span V, in this case R3. If the answer is no, then we're going to say that no, the vectors do not span R3. By the way, I should mention here, guys, that mathematicians are often made fun of, I guess, sometimes compared to, say, engineering or physics or other applied sciences, because you notice that the mathematician doesn't care about solving the system. They just want to know, can you solve it? We're not actually going to solve it. I just want to know, can I solve it or not? And if I can, fine, I won't do it. If I can't, then, oh, that's too bad, right? But I'm not actually going to try to solve the system. It's just yes or no. In other words, what we're really asking is this consistent? Actually, this looks like one equation. Does it look like one equation to you guys? But I can actually tell you that that's actually 3 equations. Because there's a left slot, there's a middle slot, and there's a right slot. And all 3 slots actually create an equation. So I'm going to take this boxed equation and I'm going to make 3 equations out of it. So if I go with the left slot, I'll just write left here. If I go with the left slot, let's just read across the left slot of everything. So if I go across the left slot, I've got 2C1 and then plus 3C2 and then plus C3, that equals X. So just so it's clear to everybody what I'm doing, I'm just looking at the first slot here. I'm going to underline it in blue. The left slot of every single part of that boxed equation. And then we're going to have a middle slot. And if I go into the middle slot, I have negative C1 minus 3C2 plus C3. And this should be equal to Y. And then we have a right slot. And the right slot would be 4C1 plus 5C2 plus 3C3. And this would be equal to Z. So we're taking this one, is everybody following that? So the right slot, I take the 4, the 5, the 3, and the Z. You see what I'm doing? And I'm making my equation out of that. Yeah, that's how that works. So it takes one vector equation and turns it into a system of 3 individual equations. And again, all I really care about here, guys, is whether this would be consistent or not. Is it possible to solve for C1, C2, and C3? So let's come back over here. Make sure I'm not going too fast. I'm really trying to go careful today because this is really important. We're going to be doing it a lot. So don't hesitate to slow me down or ask a question if something's not clear here. But the whole idea in Math 250B is that, everything ultimately goes back to being about solving a system of equations. This is 3 equations and 3 unknowns. Remember, I want us to be careful. X, Y, and Z are fixed. Those are not the unknowns in this system. The unknowns are C1, C2, and C3. Let's write down the augmented matrix now that would go with that system. The first row would be 2, 3, 1 augmented with X. The second row would be -1, -3, and 1 augmented with Y. And the third row would be 4, 5, 3 augmented with Z. And remember, the unknowns are these C1, C2, and C3 values that line up to those columns. So we would write out the matrix like so. Okay? Now, the question we are asking, my friends, the question we are asking is it's a simple question. Is that consistent? Is it consistent? And remember, consistent, this goes back, remember the 3 outcomes of Gaussian elimination, right? No solutions, one solution, or infinitely many solutions. I just want to make sure that there's at least one solution here. That would be consistent, okay? In other words, what we would be looking for is whether there's a pivot that drifts into the far right column. Right? So let's do some EROs here today, guys. I'm gonna do this fairly quickly. I'll permute the first 2 rows. I only need to go far enough that I can kind of tell where the pivots are gonna be. So I'm gonna permute the first 2 rows because I want to get a 1 up into that upper left corner, 4, 5, 3, and Z. I'm gonna go ahead and leave that as a -1. That doesn't really bother me too much. Then I'm going to do A12 of 2 and A13 of 4. I'll do these together. So I'm going to leave the first row the same. And I'm going to take double of the first row and add it to the second row. Doubling the first row, adding it to the second row, I should get 0, -3, 3, and doubling the first row, adding it to the second row, this becomes X plus 2Y. Okay. And then I'm going to take 4 times the first row and add it to the bottom row. So 4 times the top row, that's because of the -1 and the 4. So I take 4 times the first row, I add it to the bottom row. I get 0, -7, 7, and Z plus 4Y. Something like that. Okay. Now, the next thing I'm going to do, I think I'll just do it right here. You kind of see the -3, the 3, and then the -7 and the 7. I'm going to do a weird ERO because I want to get this wrapped up quickly. I'm going to do -7/3 times the second row and add it to the third row. And the reason for doing that is that it'll just make 0, 0, 0 here. So let's just recopy the first row. And let's recopy the second row. Those 2 rows are not changing. But now the third row, if I take -7/3 times the second row and I add that to the third row, I will get 0, 0, 0. And what am I going to get down here? Oh boy. Let me just put a little star here and let's write down what the star would be. We already have Z plus 4Y. And we're adding -7/3, so that would be -7/3 times X plus 2Y. That's what the star would be. I just didn't have enough room to fit it right here. But now let's circle our pivots. I have a pivot right here. I have a pivot right here. And this will also be a pivot. By the way, the pivots are supposed to be 1s. But it doesn't really matter. All I need to know, remember, as a mathematician, I'm not actually going to try to solve this system. I just want to know, can I solve it? And what is the answer? Can I solve this system? Say it again. No, I cannot solve the system. How come? I have a pivot in the far right column, right? I have a pivot in the far right column. This is, whenever you see that, guys, whenever you see a pivot in the far right column, your system is inconsistent. It is inconsistent, right? That's the conclusion here. It's inconsistent. And so the answer to the original question over here then becomes a big no. It is a big no. I don't actually need to go any further with any of my work. Even if it was a yes, we would not be required to actually solve this system. We would just say, look, it's consistent, and so the answer is yes. Right? So this is just yes or no. It's a 50-50 game, right? Yes or no. And it all just comes down to whether there is a pivot in the far right column. But now what I want to do for you guys is, well, first of all, are there any questions so far? I'm just so excited. Audrey?
There's technically like there's probably one occasion where that bottom pivot could equal 0, and then the system wouldn't be consistent, but there's a lot of situations where it wouldn't be 0, right? So
Okay, so good point. Audrey is noticing that maybe for a lucky choice of X, Y, and Z, this star actually would be 0. And she's right. There could be, and I don't even know what they would be, but actually, this is going to be the equation of a plane. It's got something times X plus something times Y plus something times Z. If you set that equal to 0, there will be some values of X, Y, and Z that will make this equal to 0. And if this was 0, then we'd be good to go, and it would be consistent. But all that would be saying to us is that these three vectors span some points of R3. Like for specific X, Y, and Z that maybe fit on this plane, yeah, then you could span those. But you're not going to span all of R3 because there will be a lot of bad choices of X, Y, Z where this expression that I've called this little star here will not be 0. And if there's even one of those, if there's even one point that we cannot reach as a linear combination of those given vectors, it's not a spanning set. But you bring up a good point. I can take these three vectors and I can throw the word span in front of them. Right? I can take the span of these vectors. It's not that we can't do this. I can still take the span. I can take the span of anything. Take a handful of vectors, take their span. I can definitely do that. But what we're saying is that that span will not be the full R3. It will be some subspace. Remember, a span is always a subspace. It'll be some subspace of R3. Actually, I can tell you exactly what it will be. It'll be a plane. It will be a plane. These three vectors, they do not span R3. They are not a spanning set for R3, but they will span something. They'll span some plane. Goes through the origin, of course, because it's going to be a subspace, so it has to have the 0 vector in it. But those three vectors are all lying in this plane. I'm not going to try to draw the plane right now, but there's a plane there that those three vectors are all living inside of. This makes some sense? Yeah, Audrey.
what we're given that the difference between span and spanning set, span of it is subspace,
Mm-hmm.
but the spanning set means it's covering all of.
It's not a spanning set for R3, right? It does span whatever it spans. Because if you take any set of vectors, they're going to span whatever they span, all possible linear combinations of those vectors. It's just that in this case, it's not the full R3. That's my point. Now, guys, before we take a break today, I would like to streamline this problem over here for you. Let's go back to the matrix that we started with right here. Do you see the three original vectors in this matrix anywhere? Take a look at the matrix. Take a look at the three vectors that we started with. 2, -1, 4, 3, -3, 5, and 1, 1, 3. Do you see them sitting over here, Eduardo?
Is it like a transpose?
Yeah, so where are they in this matrix? They are the columns of this matrix. You know what, guys? That's no accident. That is actually always going to happen. When you take your vectors and you want to test them for being a spanning set, they will end up in the columns of a matrix. Why am I telling you that? Because you know what? You actually don't need to do any of this work right here at all. Because you can jump straight to the matrix and just put your vectors directly into the columns of the matrix before you even start. I'm saving you some work, okay? What's the answer to every problem in Math 250B? Throw it in a matrix, okay? And now I'm seeing that yet again. We can actually, if you want to, go straight to this matrix, okay? Without doing all that left slot, middle slot, right slot thing. You can skip that, right? So do you see it? Right here, this is V1. Right here, this is V2. And right here, this is V3. Those are the three vectors that we had been given in the first place. This is not just a lucky accident on this problem. That is going to happen on all of these examples. Okay, that's my first point to make your life a little easier. I'm going to give you another point to also make your life a little easier with this. You notice how I was really careful in this far right column. It started out as XYZ. And then we started doing our EROs, and we can see that this far right column is getting kind of messier as we go, as we do the EROs. But you know what? We actually don't care what these expressions are in the far right column. They're going to be some alphabet soup of X, Y, and Z, right? You're going to start doing linear combinations of X, Y, and Z, and that's all that you're going to have here. What is important, though, is that these far right entries are never going to be zero. Right? The X, Y, Z are going to stay in those expressions. So you know what you can do to make your life a little easier? And I will be doing it from now on, is you don't really need to keep track of the letters themselves. You can just say, look, there's something here, something here, something here. And then when I permute two rows, okay, then those things in the far right column might change a little bit. And then when I do another ERO, they might change again a little bit. But I like to just use these number symbols, knowing that it doesn't really matter what the exact expression with X, Y, and Z is. I just have to know, well, there's something over here. And if my pivot lands on a number symbol, then the answer is no. So you see, you make your life so much easier. You don't really have to keep track of what's going on in the far right column. You don't really have to do this big, long setup process. We can make this fast and easy, right? So let me just show you one more example, and then we'll take a break. And I'm going to do the example in the next example with the streamlined approach. We're going to go fast on this one. Okay, let me move this over here. I'll show you really quick, and then we'll take a little break. So as usual, we end up with a system of equations, but all we care about here, guys, is whether it's consistent or not. That's all we care about. So here's another example. Is the set 1, 1, 1, 2, 2, 2, 3, 3, 3, and 4, 4, 4, is that a spanning set for R3? Is that a spanning set for R3? Okay. 1, 1, 1, 2, 2, 2, 3, 3, 3, and 4, 4, 4. So you ready for the Reader's Digest version of the solution here? Now we're going to do it the fast way. We're not going to set it up again. We're just going to go straight to putting the vectors into the columns of a matrix. We can directly go to that. And we're going to, so the vectors go into the columns, right? It will be the same. If you write it all out again, you'll end up at the same place. You'll end up with exactly that matrix. And then in the far right column, instead of worrying about X, Y, Z, I'm going to go number symbol, number symbol, number symbol. And I'm doing this because, and this, by the way, you won't find this in the book written this way. This is, after teaching this 30 times, I figured out that it's much more of a headache to keep track of all this alphabet soup of X, Y, and Z. So let's not do it. Let's just imagine those are number symbols. And now I'm going to do my EROs directly. I'll go straight into my EROs. I'm gonna leave the first row the same. 1, 2, 3, 4, augmented with a number symbol, okay? And then can you see that, what is it? If I do A12 of -1 and A13 of -1. So I just take the negative of the first row and add it to the second row, I'm gonna get 0, 0, 0, 0. And guys, when I write number symbol and number symbol, I'm not thinking of that as, oh, I take the negative of the number symbol and add it to the number symbol. I just know that this is some other expression. What I'm trying to say is you don't have to think over here. The far right column, you just keep writing the number symbols. You don't worry about what the ERO was. So you're just gonna do this, right, all the way along the line. And so there's your pivot right there. It's in the far right column again. So is this a yes or a no? This is a no. This is a no. It is inconsistent. It is inconsistent again. It is inconsistent again. Actually, we kind of knew that that was going to happen. Because actually, if you think about it, the vector 1, 1, 1 looks like that. The vector 2, 2, 2 just looks like that. 3, 3, 3 is just like that. Notice that these vectors are all pointing in the same direction. So how are you possibly going to take linear combinations of them and get something that's over there, or over there, over there, over there? You're not. The only points that you can manage to hit or span with these four vectors are going to be vectors of the form x, x, x. And actually, if you did keep track and you put x, y, z here, then what you'd have here is x, and it would be y minus x, and this one would be z minus x. And you would say, yeah, okay, the only way for this to be consistent would be if x was equal to y and x was equal to z. In other words, all three slots were the same. These are the vectors that you can reach by taking linear combinations of the set that we were given, but nothing else. Nothing else. Does it make a little bit of sense? You guys think pretty good. Let's do. I want to do one more before I take a break. I'm sorry. I just both of these examples were in R3. Of course, that's not the only universe that we know about. So I would like to give you one where it's a different type of vector space, but the process is the same. So we're gonna do it real quick. Okay, so here is another example, and then I promise we will take a break. Here's an example. Is the set of 1, 2 plus 3x, 4 plus 5x plus 6x squared, 7 plus 8x plus 9x squared plus 10x cubed. Are those four polynomials a spanning set for P3 of R? Okay. So to solve this one, now we're working not with vectors in R3, we're working with polynomials. But it's the same idea. I have my four vectors, I can call them V1, V2, V3, and V4. I have four vectors there, and I can lay them out. I'm gonna go straight to the matrix, right? I can lay these vectors out into the columns of this matrix. Now, the issue here is how does that look when you have polynomials, right? You're not actually going to be putting powers of x into this matrix. It's literally just the coefficients that matter. So like the number 1 here, this first vector, I can think of that as 1 plus 0x and 0x squared and 0x cubed. And the coefficients that make up that number are the 1, 0, 0, and 0. So that is actually the way we're going to represent this polynomial, which is just 1. And similarly, when I go to 2 plus 3x, I'm gonna write that, it's got a constant term of 2 and then an x term of 3, no x squared and no x cubed. So the second vector goes into the second column, but not literally into the second column. It's the coefficients that will end up in the second column. If you set up another equation like this, right? If you go back and do it from scratch again, the way we did the first example, you're gonna realize that the powers of x don't really show up in setting the left-hand side equal to the right-hand side. All that's really gonna matter are those coefficients you see. Right, so anyway, so I keep going, 4, 5, 6, okay, so that's 4, 5, 6, and 0. And then the last one, the fourth vector would look like 7, 8, 9, and 10. And I augment that with number symbols. I put my number symbols down just like so. And the beautiful thing here is that I can already, without doing any EROs, I can already kind of circle my pivots. I can see where those would be already. Okay, so again, the unknowns, in case you're losing track right now, what the unknowns are those constants that you don't really see in most of the calculations, C1, C2, C3, and C4. Okay, so here's my question. Is this set going to be a spanning set? Yes or no? It's a yes. It's a yes because look, guys, no pivots have gone into the far right column. So this one would be a yes. Right? This one would be a yes, and we can see that it is consistent. Again, we don't actually want to solve the system. Mathematicians get a hard time for this. Like, we just want to know, can we solve it? And once we know, that's it. We're done. Okay. Yep, we can solve it. So we'll say yes, and we're done. So we have a spanning set. What do you guys think? Are you understanding? This is skill A over here. Given a set of vectors, decide yes or no whether those vectors could span V. And the process is lay your vectors column-wise. By the way, I see people get that mixed up because, you know, when we were doing the systems of equations, we would lay out the equations into the rows of a matrix. Now, all of a sudden, this is the first time we're seeing it. The vectors are getting laid vertically into the columns of a matrix. That's a little different. That's a little different. So just get that clear for yourself because that is a slight change from what we were doing before. Okay, let's take a 10-minute break, 11:15-ish or so. We'll pick things up from here, but hopefully, unless there's any questions, hopefully you guys are feeling pretty good about this. Okay.
Yeah. No, like I wouldn't remember it off the bat, but if I looked at the formula and just saw one example of how to do it, I think I'd be like, oh yeah. I already- Who?
Yeah. Well, I think the thing is, it looks like it's like, oh, we didn't have.
Yeah.
Yeah.
No.
She's nice and hard.
She's really sweet. But yeah, she also has this as like a brush pen somehow, and I don't really know how she did that.
Like, sometimes she'll like, I can't tell what's in the makeup.
Oh, yeah.
And then I get confused. I should have stayed one, but stayed because I'm scared.
Yeah. I'm like kind of nervous for finding internal.
I remember saying that. I do remember saying that.
Maybe it's because
Huh?
it's like
It's the same
every
class.
and you have to mix solids is so easy compared to everyone else. And I fluids is harder.
I feel like this is like statics for me. Like I hated statics. I just don't have the content. That's my problem. Like this is just something that doesn't work in the algebra. And it's a lot of memorization. Yeah, I had to retake that.
But I had something happen where I couldn't.
Yeah, I guess they're right.
You know, but
I feel like this is like statics on steroids.
it is. It is. But that's also why I find it easy because it's like stuff we never even learn how. It's like kind of a liquid function.
All right, everybody, I think I might go ahead and gather a second. Hopefully you're ready to go here for another half hour or so. Yeah, I tried to summarize for you over here what the last half hour has been about. It's actually very simple. If I give you a handful of vectors and I want to check whether they are a spanning set for V, I have a perfect recipe for doing that. We're going to take those vectors and we're going to lay them out into the columns of a matrix. So I put bars here to just kind of separate the columns. It's just to show the different columns there. The first column is V1, the second column is V2, and so on. You lay your vectors out into those columns. And we're going to augment this matrix with this column of number symbols, okay? Which is like a vector of number symbols here. And what we're going to do is we're just going to work on solving that system. Except we're not really going to solve it. All we really want to know is whether it is consistent or not. And that just hinges on whether a pivot would make it into the far right column or not. So you have some coefficient matrix here. This is, I'll call this capital A. You've augmented that with these number symbols, and you're just asking, is it consistent? Yes or no? Okay. Remember that no just means pivot in the far right column where those number symbols are. Those number symbols, by the way, you should never assume that they're zero. They're going to be some alphabet soup expressions involving the variables x, y, z, or however you defined an arbitrary vector in your vector space. Okay? That's a nice summary. Now, somebody during the break came up and asked me a question, which was actually a very good question. He said, if the coefficient matrix A is actually a square size, so you notice it has n columns here. That's because I have n vectors to place in those columns. But if the matrix also happened to have n rows, if it happened to be a square matrix, so this is just a remark I'd like to add here, guys. The remark is that if A is n by n, which is square size, is there something that we can do when we have a square matrix that we can't normally do for regular matrices? There's something that we learned that only works for a square matrix. Taking an inverse, and taking an inverse, how would we know if the matrix has an inverse? Take the determinant, right? We could take the determinant and see if it was zero or not. You know what? We can actually do that here. We can actually do that if we take the determinant of A. So if A is a square size matrix, then this yes and no business here is going to hinge on whether the determinant is not zero or is zero, right? Then, so in other words, what we can say is that it will be yes if and only if the determinant of A is not zero, and it will be no if and only if the determinant of A is zero. So in other words, we don't really even have to do any EROs. If it's a square size coefficient matrix, we can just take the determinant of it. This should make sense to us, right? Because if the determinant is not zero, then that means that when you do row reduce the matrix, you'll get pivots right down the main diagonal, right? Right? I mean, we just did one right before the break, right? It was 1, 2, 3, and then 4, 5, 6, and then 7, 8, 9, 10. We just did this one, and we augmented it here with the number symbols. This one's already in your notes. And this is an invertible matrix. The determinant is 180, in fact, right? The product of the main diagonal. So when you have a non-zero determinant, that means your pivots are gonna look like that. Which means that they're not in the far right column. That's consistent. That means is yes, we have a spanning set. On the other hand, if the matrix has a determinant of 0. If the matrix has a determinant of 0, that means it's not invertible. It means if you start doing EROs on your matrix, you will get a row of zeros. So you'll get 0, 0, 0, 0, 0 on the bottom row, and then the pivot will drift over onto that number symbol. You see? So whenever you have a coefficient matrix that happens to be a square size, I want you to always be thinking back to the tool of determinants. We can't use determinants if it's not a square size matrix, but if it is a square size matrix, feel free to use that. Feel free to use that remark, okay? So for a square coefficient matrix, the A here does not include the number symbol column. It's just the vectors on the left side. So if that's a square matrix, you can get a quick answer to this yes/no spanning set question. Clear enough? Okay. Well, I want to take this a step further with you now, okay? I want to take this a step further. Obviously, having a spanning set for a vector space is a good thing. We're pretty happy to have that, right? But one way that you could imagine making a spanning set, but let's just do a quick example here. Let's just suppose we had R2. And let's suppose we want to make a spanning set for R2. So I could grab a vector. Remember what we're going to do is we're going to put our vectors into the columns of a matrix. So let's say we take the vector 1, 1, and we take the vector 2, 2. And remember that the far right column will be number symbols. Okay. I have an idea though about how I could get a spanning set for R2, which is every time so far I don't have one, by the way. 1, 1 and 2, 2, that's just this vector and then this vector. It's not going to span anything except that line so far. But you know what? What I could do if I really want to span R2, I could just say, well, let's take another vector. Let's just take another vector, and if that's not good enough, let's just take another vector. Notice that every time I throw another vector in, every time I decide I'm going to add another vector, I'm making these numbers up. Make another vector, make another vector, make another vector. Every time I throw another vector in, do you notice that your number symbols are shifting further to the right? What are the chances that you're going to get a pivot way over there, right? When I have a very wide matrix, of course, in this case, it's going to end up being in the third column. Of course, if I have more and more and more and more vectors, right, then the chances that you're going to get a whole row of zeros down here and the pivot is going to end up on the number symbol goes way down. So if I really wanted to span R2, why don't I just grab 5,000 vectors? Just take 5,000 vectors out of R2, surely that's going to get the job done, right? Just take a ton of vectors. Some massive number, that'll be a spanning set. If your goal is to come up with a spanning set for your vector space, just grab a whole truckload of vectors, right? Chances are really good that you're going to win, right? That you're going to get a spanning set that way. Except that I'm going to change the rules of the game on you now. I'm going to change the rules of this game. And the rules now are going to be that every vector that you put into your spanning set is going to cost you $1,000. It's going to cost you $1,000 for every vector in your spanning set. So you really would like to span your space efficiently. You would like to find a spanning set that is efficient, not using a whole truckload of extra vectors that you didn't need to, right? So what I'd like to do here is move on to this next section where I'm going to address this issue. It's something called linear dependence and linear independence. And this can be kind of abbreviated. These are long words and I don't like to write them down all the time. So you're gonna see me abbreviating linear dependent with LD. And you're gonna see me abbreviating linear independence with LI. I'm going to be using LI and LD to denote these concepts. And overall, I want you to be thinking linearly dependent is generally should be thought of as a bad thing. Linear independence is generally to be thought of as a good thing. Okay, so what our goal is actually going to be, what we are actually going to try to do is we're going to try to find a spanning set for V that is actually linearly independent. Not just a truckload of vectors, which costs us $1,000 per vector. We're going to try to efficiently span V with as few vectors as possible, right? So the goal is given the vector space V, find a spanning set that is as efficient as possible. As efficient as possible. See, even in this little example here, I could take the vector 4, 5 out of this and the vector 9, 7. I could take these out. I could go back, get my $1,000 back for each of those vectors. I still have a spanning set. In fact, I could get rid of this one too. I still have a spanning set because I don't have a pivot going into the far right column. Pretty nice. So this is going to be our goal. Given a set of vectors, we would like to make an efficient way of spanning. Sorry, given a vector space, we'd like to find an efficient spanning set for that vector space. Okay, so let's write down a definition of what linear dependence is and linear independence and try to understand this concept a little bit. All right, I'm going to do that maybe right here. So let's put a definition here. Okay, so here's the definition. A set consisting of the set V1, comma, V2, comma, dot, 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 up to Vn. This is a set, is LD, linearly dependent, which is bad. We don't want linearly dependent. But what it is if at least one of the vectors, can be expressed, as a linear combination. Okay, so we've seen that word before, linear combination. If one of the vectors can be expressed, at least one of the vectors can be expressed as a linear combination of some or all of the others. If we can do that, if we can express at least one of the vectors as a linear combination of some or all of the others, we're going to call the vectors LD. Otherwise, this set, right, V1, comma, V2, comma, dot, 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 up to Vn, otherwise, this set is Li. So every set of vectors is either LD, which is bad, or Li, which is good. Okay? So we have the definition here of linear independence and linear dependence. And let's maybe do an example to illustrate this. Kind of get the idea here with an example in mind. So for example, the set, let's make the matrix 1, 2, 3, 4, and then comma 10, 20, 30, 40. That set of vectors, so we have a couple of 2 by 2 matrices for this example. Would this be would you consider this Li or LD? Can I write one of those vectors in terms of the other or not?
Yeah, you can.
You definitely can. And if you can do that, if you can write one of the vectors in terms of the others, then this set is LD. Right? And what I'd actually like to do, I'm going to label my vectors here as V1 and V2. I would actually like to write how I can express one of the vectors in terms of the others. And I think you guys can all kind of just see it by looking at this, because I tried to make the numbers really nice. Right? So what you can see is that the second vector is literally just 10 times the first vector. So this is the point that I'm making here. And so this is a bad thing. LD is bad. Why do I say it's bad? I say it's bad because you just spent $2,000 right here, right? Every vector that's in your set costs you $1,000, but wait a minute, you didn't need to buy the second vector, because you can make the second vector by just taking the first vector and scalar multiplying it by 10. Right, so that's the idea, is you don't want these linear dependencies. You don't want unnecessary vectors in your set that you could have already produced with what you had before. So here we have an example of a linear dependency. Let me show you one more. Let's do another example here of a linear dependency. Let's take the set, we did this one before. So this is coming back into your notes again, just to show it to you one more time. The set 1, 2, 3, 4, 5, 6, and 7, 8, 9. And you may remember that with this one, we actually took we put this into a 3 by 3 matrix, and we took the determinant and we got 0, which is kind of a bad thing. And what it reflected was the fact that, yeah, this set is also LD. This set is also LD. And once again, I would like to write out what the relationship is. So let me label my vectors again. Again, we did this one about a week ago. I just want to get it back on the board for you here one more time today. So take V1, V2, and V3 like so. And then what you might notice, this one's not as obvious. It's not as obvious, but the third vector, V3, can be written as 2 times the second vector minus the first vector. So if you do the little mental math on that, if you double the second vector and then subtract the first vector from it, you'll get the third vector. Right, V3. Another way to say it is if you take the first and third vector and add them together, you get 8, 10, 12, which is exactly double of the second vector. So this is another example of a linearly dependent set of vectors. By the way, these vectors are also not going to span R3. If you lay them down, just as a note here, if you lay them down into the columns of a matrix, 1, 2, 3, and then 4, 5, 6, and then 7, 8, 9, right? And then you augment with number symbol, number symbol, number symbol. The point is that the determinant of this little matrix, you guys can check this if you want to. It's a little 3 by 3. You can use the arrow method. That determinant is going to be 0. That's a bad thing, right? When the determinant is 0, then what we said is no, 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 it's not a spanning set for R3. And in fact, these 3 vectors basically span only a plane. And a week ago on Tuesday, I actually wrote down the equation of that plane for you. We actually wrote it down. So this is not a spanning set for R3, which is bad enough to begin with. And we've spent $3,000 when we really didn't need to, because the third vector is dependent on the first 2. It doesn't help us in any way with trying to span our space. In fact, if we did the EROs here, I'm not going to fully do them, but what you would come up with here, guys, if you actually tried to row reduce this, you would get something that looks like this. I think it's like -3 and -6 and then number symbol. And the bottom row would be all zeros and then number symbol. So this would be how your pivots would end up if you actually did the EROs. And so what you can see here is obviously it's not consistent. So these vectors, let's just add this up here, not a spanning set for R3. What we were talking about earlier today, this is not a spanning set for R3. And we can actually identify which vector is the culprit. We can actually say, we got 3 vectors here, like which one is causing the problem? Like which one should we take out and get a refund for? Go get our $1,000 back. Well, it's going to be exactly whichever columns don't have pivots, right? So this third column, which came from this third vector, is the problem. That is the, if we said, oh, I want to go back for a refund, I don't want this third vector now, then when I set up my matrix now, I would then not have this column anymore. Okay, it's no longer a square matrix, so you can't take the determinant, but I can promise you if you do the EROs, now you're going to be really happy because you will have no unpivoted columns here on the left side of the bar. Right, so that's kind of the idea. So you can take that guy out and say, yeah, I don't want to spend an extra $1,000 on that one. Okay, so that's another example of a linearly, it's a bad set of vectors, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 3 bad vectors. They don't span R3 and they are LD. It's like worst case scenario. Our goal is to find a spanning set and to make it efficient. We didn't find a spanning set with these vectors. And it was not efficient because the vectors are LDs, like really, really bad. Really bad example. Question, yeah, go ahead, Audrey. Yeah, because we took the determinant and we got, well, you could say we took the determinant and got 0, or you could say we did the EROs and there was a pivot in the far right column. Either way you want to say it, it's all consistent. It's all compatible. I shouldn't use the word consistent. It's not consistent. The system is not consistent. Okay. Do you want to see one more example of that, of this linear dependence idea, or you kind of have the idea here so far? One more. Okay, let's write down one more. Let's do a polynomial example. Let's take the set of 1, comma, 1 plus x, comma, 1 plus x squared, comma, 1 plus x squared plus x cubed, comma, x plus x cubed. So that's actually 5 vectors. Let's label them maybe V1, and then V2, and then V3, and then V4, and then V5. Label my 5 vectors like so. And I'd like to try to figure out whether the vectors are Li or Ld. Are they good or are they bad? Again, it's maybe not obvious to you, but if you take the second one minus the first one, the second one minus the first one is x. And then take the fourth one minus the third one. So forget about that. Then just take the fourth one minus the third one. What do you get? You get the fourth one minus the third one. What's 1 plus x squared plus x cubed? And then subtract 1 plus x squared. X cubed, right? So the second one minus the first one is x. The fourth one minus the third one is x cubed. And so combining that, you can actually make the fifth one as an expression involving the first 4. So let's write that down. Let's just note that V5 is equal to V2 minus V1 plus V4 minus V3. So if I just play around with the equations like so, I get, yet again, I find out that these vectors are LD. Again, it's a bad set of vectors. Again, it's a bad set of vectors. Now, in this case, though, actually, this set of vectors isn't quite as bad as the last example, because in this case, I actually can tell you that these vectors, they will span our P3 of R. If we lay these vectors down into the columns, so we write down, we did this just before the break, we did one like this. If we lay these vectors down like so, right? This is how the matrix would look, and then we would put our number symbols over here again. The nice thing, at least in this case, when I circle these pivots here, I don't get a pivot in the far right column. So it is a spanning set. This is a spanning set. So this implies that we have a spanning set for P3 of R. We're getting lots of examples out of all this. We do have a spanning set for P3 of R here. Everybody understands how I made this matrix? The vectors go into the columns. V1 goes right there. V2 goes right there. V3 is here. V4 is here. And V5 is the last column with just the coefficients of the x's going vertically into a column. Okay. So this one is a spanning set, but the problem is we spent $5,000 on it when it should have only cost us $4,000. You can see that if we removed the fifth vector, if we go back to the store and say, I don't want that last vector anymore, you get rid of this fifth vector, then you would essentially get rid of this column. And if you get rid of this column, then it's still consistent, right? Getting rid of this column does not destroy the spanning set property. You can still span the full P3 of R, even with just the first four vectors. And that's really your clue that the fifth vector was costing you too much money, right? An extra $1,000 that we did not need to spend here. That's right. That's right. Okay, so so it's a spanning set, which is good, but it's linearly dependent. So now I just want to express for you how you would write up, or I mean, what if you didn't just see this? What if you didn't just, I mean, this one was pretty easy. Second vector is 10 times the first one. What if you didn't notice this equation? What if you didn't notice this equation? How are you going to figure this out without having to sort of be a genius and like look at the vectors and say, oh, I can see that these are combinations of each other. So let me rephrase, hold on a second, Audrey, I'm going to just rephrase the LD and LI. Okay, so we're just going to rephrase it here, what these things really mean. So the set V1, V2, and ... up to Vn is LD if and only if. Okay, so I'm going to write it a little differently. There exist constants. I'll write it down and then I'm going to explain it for you. There exist constants. This would be C1, C2, and so on up to Cn. And the most important words that I'm putting in this definition right now are the words not all zero. There are constants, not all zero, such that if we take C1 times V1 plus C2 times V2 plus ... plus Cn times Vn, that we do get zero. That we do get zero. So the vectors are LD if and only if you can find an interesting way to make them cancel out. Of course, I could put 0 in front of every vector here on the left side, and of course that would give me 0. What we're saying here is, can we make the vectors cancel out in an interesting way? So all I'm saying, let's look at the 3 examples because that makes it super easy. All I'm saying here, guys, is like on this first one, 10v1 minus v2 is equal to 0. You can just move everything to one side of the equation. So in blue, I'm going to go through all 3 examples, and in blue, I'm going to rewrite the boxed linear dependencies that we wrote down earlier in this rephrased format. In the rephrased format, I'm required to have 0 on one side of the equation. So this first example, we originally said that v2 was 10 times v1. Well, I can rewrite it like so. The second example, let's see, I can rewrite this one as v1 minus 2v2 plus v3 equals 0. So you're moving the vectors all to one side of the equation. So that would be the linear dependency there. And then on the last one here that we just did, again, I'll move everything to the left side. v1 minus v2 plus v3 minus v4 and plus v5 equals 0. Every example on the board is LD. We don't have any LI examples yet, but they're all LD. And this is called, there's a name for this. This is called a linear dependency. And this is called a linear dependency. These are linear dependencies. And this one is called a linear dependency. These are all bad things. We do not like linear dependencies. LD is bad. We spent too much money trying to span V with our vectors. Okay. So why did I rephrase this definition in the blue way, these linear dependencies? It's because we can actually go through a systematic process to create these, to discover these linear dependencies. We can actually go through a systematic process to do it. I think because I'm close to out of time, I don't really have time to explain it right now. I might have you watch a little video this weekend, just where I'll just explain. It won't be long. It'll be just a quick, how do you quick and dirty do these LI, LD things from a practical point. I've explained the concept of it already. It's really just, so how do you, if somebody hands you a set of vectors, how are you supposed to decide if they're LI or LD if you don't just glance at it and figure it out? Like, there is a process, and you know what the process is going to be, right? Put it in a matrix. You're going to take your vectors and you're going to basically do this. You're going to basically put them into a matrix, except there is one big difference with the LI/LD question, which is you will not be using number symbols in the far right column, because you're not interested in making a linear combination add up to an arbitrary vector in V. You're interested in having your linear combination add up to 0. So we'll be setting up the same matrix, but instead of number symbols, we're going to be putting zeros over here in the far right column. And instead of asking whether it's consistent or not consistent, we're going to be asking whether there are any free variables or not. Free variables, like we see here, this column gives us free variables, is going to be a bad thing. Free variables means there's lots of solutions for these constants that are not just zeros. And that means LD. If there are constants that are not all 0 that solve your system, that's bad. So free variables in this context will actually be bad. I am probably going to make a little video of that and show you an example or two. I could just use these same examples actually. So I'll make it short, but I'd like you to do that. Guys, I didn't have a lot of folks come into my office hours about this homework, so I am going to see whether today I might have some office hour activity. The homework is due tonight. You have till midnight and I'll be around all evening. Jump into Zoom with me, stop by. It's not, there's some questions over there. If I had more time, I would have done them today. But we needed to cover this material. So please stop by and get some clarity about the homework. Don't just blow this one off. There's definitely a lot to learn. Okay? With that, I'm gonna let you guys go. Thanks for a great day today and have a good weekend if I don't see you before then.
Excuse me?
Yeah.
So I saw for your office hours, I thought it was from 8 to 10. Was it?
Tonight, no, on Thursdays, it's from 5:30 to 7, and then from 8:30 to 10. 5:30 to 7, and then from, I think that's what it should say on the,
Cause I was.
on my syllabus?
Yeah, cause I put midterm, so.
Oh.